Greetings all. In this video, we're going to do a short and sweet example for regression, a simple linear regression model, an example that's provided by the render et al. Text that I think is really representative of a simple relationship that, upon inspection of the raw data, the pattern or the relationship might not be completely obvious. I'm going to share these slides for anybody that is interested. So don't worry about actually capturing any of the data as we go through this. I'm necessarily going to move through it pretty quickly because I think the reality is not many of us are going to do these types of calculations by hand. So it's going to serve just as illustrative purposes, and then we'll jump into the software and see how we can do it much quicker. So the scenario we have a sales manager. She is running some newspaper ads and trying to fill up her apartment complex. And she's interested in the relationship between the number of ads that she's running the month before and then the next month's rentals or leases. So just two variables, right? This is a simple linear regression example. We just want to see, and is there a relationship? Is it statistically significant? And what can we say about that relationship so that we could make maybe some predictions for the future? So here's the raw data. We have, for an independent variable, we have the number of ads purchased in the newspaper. So, whatever periodical that she is choosing, we have some ads that we're running. And then we have the raw data for the number of apartments leased in the complex. Very simple situation, but unless you're much more quantitatively savvy than I am, I simply can't just look at this table and tell you what the relationship is. That's a little bit beyond my capability. So we'll go through the process and do some simple calculations and see what we can figure out. Just as a reminder, these are the equations. These are given in the render et al. Text. As you can see, we've talked about before that these are not terribly complicated, just simple adding, subtracting, multiplying, and dividing. But that'll give us the information that we need to examine the relationship between the number of ads run and the number of rentals. So keep that in mind as you start going through this. And like I said, I'm not going to spend a whole lot of time going through these calculations. This is simply a table that gives you a running sum of the calculations that we're doing, or that you should be doing in a simple linear regression situation. They're pretty self-explanatory. Plus, I don't expect a lot of people will be doing this by hand, so we'll move through this pretty quickly. If we take some of the sums that the work that we did on the previous slide, here's the information that we have. Using this information, right, these totals, we can compose our line of best fit. So our line of best fit, or our estimated regression equation, is given as y hat is equal to 0.915 plus 0.395x. Or another way to look at that is very simply, the expected number of apartments leased is equal to 0.915 plus 0.395 times the number of ads placed the month before. Okay. Keep in mind, as you probably already read, we can make some predictions using this equation that are beyond the scope of the actual data. And we just do that by plugging in numbers for the ads placed, right? So any number that we can come up with for ads placed in the month before, we can generate an estimated number of apartments leased based on this equation. If we take it a step further, we're interested always in the coefficient of determination, or our R squared, and we're interested in our correlation coefficient, right? That rough measure of the relationship between the variables we're interested in. If we were doing that by hand, we could generate a table like this. get the components that we need. The results are given here, the R squared at 0.81, and that's rounded to 2 decimal places. And then we would take the positive root, square root of the R squared to get our correlation coefficient, and that's given as R equals to 0.9. Okay. Again, these equations for the coefficient of determination and the correlation coefficient are a little bit more sophisticated, I guess, or have a few more moving parts than we're typically used to, but we're not going to do this by hand. So let's jump into the software and see how we can do this much quicker. So we'll go into Excel QM. One thing that you'll need to be aware of is when you look into the actual Excel QM tab, it's not listed as a linear regression module. I'll show you where it's buried, and that's probably the most non-intuitive part of this. All right, so we've got the software opened up. We'll go to Excel QM. We'll go to alphabetical, and now you'll see that there's no linear regression tab for these calculations. There's linear programming, which is a completely different technique. So don't get confused by that. Instead, we're going to go to forecasting. And when we go into forecasting, we're going to have several different choices, but we're going to look at the regression or trend analysis. And I'm also going to show you the multiple regression tab, because we can do this calculation in either one, and they have slightly different information. And so I want to show you both, and that way, you know, depending on what information you're looking for, you'll know where to find it. But to start out with, let's go to regression and trend analysis. And so as normal, you know, we have our Excel QM start screen that's going to ask us to name a few things, to set some information, and then we have our options that we need to pick. So for the title, we'll call this simple linear regression. And for the sheet name, we'll just call this simple for illustrative purposes. We know that the data that we're using from the example has 8 observations. And then we're going to go ahead and pick the options. The tracking signal is used more for forecasting type work, but we'll go ahead and grab it anyway, because it's nice to have more information than we need than less. And then we're also going to graph it, you know, and that's important, because when we have the opportunity to visualize the data and provide another means of exploring it, it's good to do that. All right, so we get into the software. As we've mentioned before, you know, the gray spaces we tend to leave alone. The orange or light brown squares or cells, that's where we're going to plug in our data. I'm just going to move this graph up here so we can see it populate as we start plugging in our data. And then we'll get started. All right, so we've got our data plugged in. Everything's automatically been populated, and the calculations that we're interested in have already been ran. One thing that I'll tell you, and this is more of a helpful hint, and it's a reminder for myself, because I am the worst offender in making this mistake. When you're entering the data, be sure that you're putting the independent and dependent variables in the right spot. Very often, if I get in a hurry, I'll plug in my independent variables under the Y or the dependent column, and make the same mistake with the other column. Just take your time, be mindful of that. If you do these calculations, you run a data set and it doesn't look right, and there could be some issues. A lot of times what you'll find is the mistake is in the data entry. So be sure that you got the data in the right place. be sure that you've got them in the correct order and that the pairs are correct, right? You want the independent variable and the dependent variable that's associated with it to be together and in the right spot. So keep that in mind. So assuming that all the data is incorrectly, and I think it is in this instance, we'll see that we've got the calculations for the errors and some of the different things that we're going to be looking for. We can see that our graph has been populated and the line of best fit has been drawn. Down here is where we'll find the information for the regression equation, right? We've got our intercept and we've our slope. So using that information, we can plug that in and create our regression equation. And I'll just plug this in real quick. What we had in the slides was 0.91 plus, we'll just call it 0.40x, right? And so just to estimate, given the information that we have, I mean, we could go out to several more decimals. I'm just doing this for brevity's sake. That would be our regression equation, okay? Over here in the other calculated box, up top, we have our correlation coefficient, and right below it, we have our coefficient of determination, or our R squared, okay? So given the choices that we've made, and just plugging in the data, we have all the information that we need for the regression equation, and we have the correlation coefficient and the coefficient of determination, right? We've got our R and our R squared. We also have a nice little graph that shows our data and plots the line of best fit for us, okay? So, you know, in just a few steps in very quick order, we've got everything that we need to interpret the relationship between these two variables and make some assumptions. Now, one thing that you'll know is missing out of this particular screen and this particular module is we don't have that F statistic, that F test that we need to determine statistical significance, right? I'm going to show you a quick way to do that, just so you can validate your results and have some confidence that you can interpret your regression equation. So what we're going to do is we're going to go back up and we're going to go to forecasting again. And this time we're going to go to multiple regression. Now in this module, we can do multiple regression where we have multiple independent variables, which is, you know, the typical procedure for that. But we can also do it, there'll be a setting where you can do a simple linear regression as well, right? We can have just one independent variable. You have the option to set that when you fill it in. So here's our sheet name. I'm going to call this one multiple. We've got our same number of data points or periods. I'm going to use the same data. I'm going to keep this number of independent variables set at 1, right? Because remember, this is a simple linear regression example. If we had more than one independent variable, then obviously we could adjust that, but we don't need it. And then in the options here, we're going to pull this ANOVA option. And that's going to give us that F test and give us that statistic so we can determine whether the omnibus test for the linear regression equation is statistically significant. All right. So things are going to look very, very similar. You'll notice that we don't have a graph because in most multiple regression situations where you have more than one independent variable, then you obviously can't graph in 2 dimensions. But we still have our forecast and error analysis. It's going to give us our sum of squares calculations. And then down here, it's going to give us that ANOVA summary. It gives us that F statistic and that probability associated with it, okay? So I'm going to just jump over to this other sheet and grab this data. And then I'm going to bring it over here. We're going to plug that in, same data. And what you'll notice is we get our coefficients again. It's presented a little differently, but the information is exactly the same. So we've got our intercept and we've got our beta 1, right? We've got our X coefficient, okay? So we can calculate or we can state our regression equation just like we did before. It has that forecasting mechanism like the other sheet, but we're not really worried about that for right now. It does provide you with the correlation coefficient, but it doesn't give you the R squared in this one. So if we were using this, we would need to calculate the coefficient of determination ourselves. And I'll do that real quick, just show you how to do that, right? So R squared, and we'll just say is equal to the correlation coefficient times itself, right? And that'll give us our coefficient of determination. And if you go back and you look between the two sheets, you'll notice that given those calculations, the information is exactly the same. Now, our whole reason for coming over here and checking this out is because now we've got this ANOVA with the F statistic. And what this is showing us is that the F value is 25 and that the probability associated with that F statistic is 0.002, right? And so, as it mentions in the render it all text, we're looking for a probability of 0.05 or less. So what this tells us is that the test for our regression equation does indeed show statistical significance. So we can have some confidence in using it to predict and estimate additional values, okay? I'm not going to get into a protracted conversation on the F statistic because you can read that in the textbook. But unlike in the simple linear regression example where we didn't have that statistic, we have it here under the multiple regression where we can pull the ANOVA. Now, if we had multiple independent variables, not only would it give us the F statistic for the omnibus test for the regression equation, but it would also give us a t-test for the independent variables, each independent variable. And again, we'll use that to determine whether or not those independent variables are statistically significant. All right, I hope that gives you enough to start exploring and playing with some data and doing some interesting things. My recommendation is to take the example that we covered in this video and try to reproduce the results for it. It's also a good idea to take the examples that are directly in the text and see if you can recreate those results as well. I hope you have fun. Please reach out to me with any questions. Good luck.